So then, yeah. So, and then feel free if anyone else has any input on like maybe how to solve these problems if we're all stuck. Because some of these problems are relatively difficult. Feel free to kind of jump in and give us your input. Yeah. So yeah, the floor is to Justin, Sebas, and Matthew if they so choose.
All right. So number one, pretty straightforward. Just adding up capacitors. So you've got to remember it is opposite to resistors. So these two things that would normally be in series, this one and this one, if they were resistors, you'd treat them like parallel. So it'd be 2 parallel with 1 plus 1 plus doesn't like me. Plus 2. So like these three, you can just add them up together. So 2 in parallel with, this will be 4. If you work out the math, it comes out to 1.33. So B.
So what capacitors are in parallel, you just would you still you do the same as oh no wait, you do the opposite as resistors.
Opposite of what you do for resistance.
So 1 microfarad plus 1 microfarad plus 2 microfarad. And then the okay. Got it.
Yep.
This one plus and then 2. I have to do this. 2
6
over 1 microfarad.
Yep. Okay, so what are the voltages across? Questions? Get it? Simple enough?
2 in parallel. So when you have 2 in parallel with 4,
it's not actually in parallel. I just did that for like for the sake of math.
Right.
You calculate it as if it were.
Right.
Yeah, exactly.
So when you have 2, I forgot how to do, so 2 times 4 divided by 6. Oh, 2 times 4 over 2 plus 4. That's right. I'm an idiot. I forgot.
I think isn't it the other way around?
I don't think so.
No, yeah.
It's the other way around. Yeah.
Yeah. You got it.
I don't know. Is it the other way around?
So which one is it?
2.3. B?
No, it's this way, yeah. Because if you do like 6 and 6, it goes to half. So it'd be 6 times 6 over 12. That'd be 3. And that math works out right. Yeah. So it's multiplied over addition.
2 times 4 over 2 plus 4. 6. I'm making those notes right here.
The answer key says, right?
What happened?
And that is what the answer key says. Awesome. Great.
Let me go ahead and, I'm still writing that down.
Did you guys go over anything before this question?
Negative. This is our first question.
Sir.
Sorry guys, I'm fucking late, but
there he is.
Let me see one thing. Bacalino. There we go. Okay. Professor, where's the professor though?
All 3 of them are here, baby.
Oh yeah. Okay. Oh yeah. Yeah. I think Manny and Arnubio are joining right now, and Kim, and then we have Felix as well on the other quiz, and so yeah.
Yeah.
We just did number 1 right now. Just found it, equivalent capacitance.
Damn it. Oh, shit. You guys can hear me. All right, hold on. Sorry, guys.
Damn, Sean is organized for the semester.
All right. Everyone that just got here right now, you guys need a quick rundown of what's going on number 1? All right, so you're just finding the equivalent capacitance, right? So when you're doing that, you're just pretty much combining all of your capacitors together. However, when you combine your capacitors together, you do the opposite of what you would do for resistors. So when you have capacitors in parallel, you would treat it as if, or you would calculate it as if they were in series.
Okay, okay.
1 microfarad plus 1 microfarad plus 2 microfarad, 4 microfarad. And then when they're in series, you would calculate it as if they were in parallel. So it's 2 microfarad times 4 microfarad over 2 microfarad plus 4 microfarad. And then this is your final result, 4/3.
Are you guys giving out the answer like before, or?
I have the answers. I don't know if we want to, or if you want to just show them like how the book did it.
We can, I guess we can. How does everybody want to do it? Do you guys want to know the answer first and how we get to the answer, or
Yeah.
or the other way around?
The other way around.
The other way around, okay, we'll work out the answer first, and then we'll show you.
What's the number in the middle, bro, for
That's a 1.
Oh, it's a 1? Okay.
Yeah, 1 microfarad.
Oh shit, my bad.
So I
Pretty
can do
much.
the next one.
For sure. So this one's kind of weird just because like half of the questions on this page, half the questions on the next page.
Yeah. If you want, I can
Share
share
your screen?
my screen. Yeah, and then I'll just go from here.
Go for it. Whoa.
1 sec. Okay. Let me do this here. It's weird because I have to like record my screen for some reason. Okay. Can everybody see?
Yes.
Yeah.
Yes, cool.
You see your-
Okay. So here's the question. What are the voltage across and current through the 5 ohm resistor in the center leg? So what it means is what it's asking for, pretty much find IX and VX in this center leg right here. So if anybody knows anything about DC circuits and I guess passive elements in DC circuits, right off the bat, you should know that whenever you see a DC element and there's a passive element such as like a capacitor or inductor, you have to treat them in their steady state form. So when we have a capacitor, I don't know. Do you guys want me to do like the quick little background as to why, or you guys want to just jump into it?
No. Do the background.
Okay, so in a capacitor, I don't know if people care about this stuff, but DC steady state. It's called steady state. Okay. So a capacitor in steady state becomes an open circuit, and an inductor. Can you guys see what I'm writing here?
Yes.
Yes. Okay. And an inductor becomes a short circuit. So if we were to redraw this circuit over here, we notice that there's a capacitor right here. So this capacitor is going to open this circuit. So that means that everything past over here is gone. So we can automatically jump into like this super easy circuit that everybody knows how to solve, hopefully. It's just a voltage divider
Mm-hmm.
Excuse me.
Right? Everybody have any questions?
What is the equation for voltage divider?
Well, we could just do without the, if you don't, if we'll do it the organic way, and then we'll jump into the voltage divider equation.
Yes, please.
That way everybody can see both ways. Yes, and please don't
Let
ask
me,
me questions.
let me show you my model first, though. Let me show you my model.
Okay, so this is like step 2, right? Sorry. Okay, so simple. If you guys want to do it, doesn't matter. I don't care. Let's just go. Let's do like a simple mesh loop because we only have one current going through here, and that is the IX. And let's just assign polarities when you're doing mesh. Okay. So anybody want to help me? What's the equation? What am I gonna end up with?
Oh, do mesh? Oh shit.
Yeah.
Mesh.
What am I gonna end up with?
KVL, man.
Yeah, KVL. Someone,
10,
anybody.
10
What is it?
volts
Okay.
plus 5 times IX times, I'm sorry,
Yeah.
plus 5 times IX
Right. Yeah, it's perfect.
equals 0.
There we go. That's it. And there it is. We already got the whole problem right
Shouldn't
there.
it be
So,
minus? I'm sorry. Shouldn't it be minus 10 volts?
okay. Does someone want to answer him? Why it isn't minus 10?
Because there's I counted voltage drops and voltage rises, so the rises are on the left, so that's
Right,
why
okay.
10 is
Yes.
just a regular 10.
Right, right. So if I want to like maybe simplify this a little bit more, we're setting the rise equal to the drop. Do we get that? So
Real
if I'm
quick,
looking at this,
bro, I just wanted to point something out. So it looks like you have minus plus instead of plus minus on the resistors. So current is actually going against passive sign convention. I don't know if the resistors are supposed to be like that or.
Oh, you have to subtract. Yeah, that's right. He's taking the negative sign first.
No, you're right. You're right. Yeah,
Subtract those or change the polarity of the resistors.
Yeah. Okay, yeah. So we could do that. We'll add like a minus right there. You're right. Damn, it's been too long. Okay, there we go. But yeah, but the 10 is actually there. So, yeah. So we're setting rise equal to drop, and if we proceed with this, we should get 10 volt minus 5 IX. Oh, here, we'll take out the volt. Probably easier without it. Minus 5 IX. And then we're going to solve for IX. So that's going to give us 10. It's equal to 0. And as we see, it's looking like it's just going to end up being 1.
So passive sign convention says like if current touches the negative polarity, like that's
right. Yeah. So since we're going this way, right? Yeah. So it touches this first. It really just depends how you're drawing your polarities as well.
Right.
Yeah. So I should make a note. I think it's non-passive sign. I don't know what it is. I forgot what it is. Maybe someone want to check for me.
I gotta check the archives.
Yeah.
Not the archive.
Anybody have any questions?
So the polarity on the resistors is positive to negative?
Oh, it really just depends how you want to.
Oh, okay.
I could do it the other way too. Okay, so let's try.
It's because the way I see it is like I would say current travels from more to less, like water. You know, if a place is full, it goes to.
Yeah, yeah. No, you can do it that way too. It's totally like okay. We'll do it. Let's try it your way too.
So I was just gonna answer your question, Sebastian.
Oh, okay.
So what we're talking about in the last problem, it was non-passive because it touched the negative side first. I have it in my circuits notes. And if it touches the positive side, it's passive sign.
Right. So let's say he wanted it to do it this way, right? and then you have the current in there. So writing the KV out for this, now you have one rise and then two drops. And if we solve for this, we can see that it equals the same thing. So it really just doesn't matter. It doesn't matter how you do it, whatever you think is easier for you. Just remember, remember to use, pay attention to passive sign and non-passive sign convention. Okay, we good here?
I'm gonna wait a little bit just because I don't know if people are still copying or.
Yeah. I think you're going a little bit too fast. Like.
Oh, too fast? Okay, I'm sorry. Here, I'm gonna stop right there.
Yeah, because you look up and I'm trying to copy and look up and I'm like.
Okay, yeah. Tell me if I'm going too fast. If I'm not going fast enough, I'll slow down. I forgot. I'm sorry.
I'll do this professor style. So like when you're got everything copied down, when you understand it, you don't have any questions, just put the thumbs up in the participants.
Oh yeah. How about everybody put the thumbs up, that way I know when we can.
So if you feel like you're good to go, just put a thumbs up.
Yes, Devin, the answer is C.
I don't know if I can put a thumbs up. I don't think I can.
Can you go all the way to the top, to the very top, just to see what you wrote in the beginning?
I can't put a thumbs up either, but thumbs up.
Go to the reactions. It lets me. I don't know. There you go.
Cool. Okay, we actually aren't done with this problem. I mean, it asks us to find IX and VX, so we still have to find VX. But now that we found the current going through that resistor, all we need to do is use V equals IR and find the voltage.
Sorry, I'm trying to figure out how to do
So
it.
just 5.
Yes, it's just 5 because it's just 1 times. Oh, I could just do it up here. I guess.
So for capacitor, you short it, and inductor, you open it?
Capacitor, you open it, and inductor, you short. You had it backwards here. I could write it on the side right here.
So maybe I don't see it. How do we know it's in steady state?
Because, okay, steady state only occurs when there's a DC source, because there are 2 DC sources right here.
Mm-hmm.
That it just means that this is a and it also tells you in the question the circuit is at steady state.
Oh, I can barely see that. That's why.
Oh, I'm sorry. I'll just.
There you go. Okay.
Okay.
Yeah.
Sorry.
There you go. Ah.
I don't think. Okay, so.
I see. So.
I don't think I have the thing. I don't know how to do that, to be honest.
How to do what?
How to unlock because I don't think anyone can put their thumbs up or anything like that.
Oh, you gotta go to security and allow participants to react, I think.
No, it's on the more, the 3 dots. So then you have a bunch of emojis on top.
Can you do it?
I have it. Look.
Oh, you can do it?
Yeah,
Oh,
I'm putting thumbs up and.
Okay, well then let me put mine.
Did everybody get this? Does anybody want me to move down or anything?
Where do you find the thumbs up at?
The more.
Yeah.
More?
Yeah, the 3 dots, and then you're gonna see like 6 emojis you can put if you're using an iPad.
Oh, that's ghetto.
Yeah, I don't know if it's the computer.
Same.
I don't even see it.
It might be on the bottom, maybe where it says reactions. Does it say reactions or anything? Oh, there you go.
Or I mean,
just thumbs up.
Or you.
I thought it was supposed to show up in the chat though. So.
No.
That's why me too. I don't know how to make it show up in the.
Because Dr. Juan tried to make us like raise our hands and stuff in the chat, and I don't have that. Not that happens with
Should be doing
like
that
every
shit.
Zoom call.
Should be doing that shit.
Mhm.
Any questions?
Yeah, if you have any questions, just unmute your mic.
Or yeah, unmute yourself.
Let me,
There's no such thing as stupid questions.
Yeah, no,
It's
seriously,
a breeze, guys.
I've had a billion stupid questions. So,
Me too.
okay, all good on here? Oh, well, I guess we forgot to put, find.
okay, steady state. So that's why you don't consider the right side of the circuit, right? Because you went to open circuit.
Correct,
Yeah.
correct.
Raven software. Computer games.
There we go.
Oh shit.
Mm-hmm.
There we go, there's the answer. And the answer is C. Questions?
Mm-hmm.
Good?
Yeah, I am good. Mhm.
Okay.
You
All
guys
right,
have
if nobody has any objections, I guess we'll move on to the next one.
Do it.
I don't know if we'll stop broadcasting, but let's see. Oh, I don't know. I mean, we can switch off. Maybe Justin or Matthew want to do the next one.
If anything, I could just share. Well, up to you, because I could just share my screen again and then put the question up and see if Justin or whatever, or
Okay, yeah, sure.
just open it
Go
up.
ahead. Here, I'll stop.
Okay, so the next question. Oh. Oops.
I don't know how to explain this one. Matthew, you want to take it?
okay.
So this is the one we did. So here. So we're doing number 3.
The fucking Devin.
I know,
What?
bro.
What, Jonathan?
No, he said 7 in food.
7. Oh no, I said 7 and not Devin.
7 in equivalent.
I know, I'm playing.
The Devin equivalent.
Devin equivalent.
You want to take this one, Sebas?
I think let me try. Let me see if I can
Okay.
get this.
I mean, it's okay. I mean,
Can I try this first?
yeah. Go ahead. Just
I was
go
just
ahead.
thinking, like, if it's 7 in, right, you just disconnect the RL and then
Yes.
it's just an amp going through it. And since you want A to B, which is across 12, you just multiply. But is it really that simple?
Yes, it is. It is that simple.
Oh.
Talk to me.
Go ahead. Send it.
It was hard.
Okay, so what I got from this was all right. Looking for Thevin,
Okay.
right? To
I'll
the
get the
left.
next question ready.
So it just wants everything to the left. So fuck the right side. RL, it's gone. So circle, and this is just gone, right?
Mm-hmm.
So now you just have one loop with 10 amps going through it. And where do you want your voltage? Across here and here, and that's across what resistor? 12, right? So you want this. And since you have current and you have resistance, what's voltage?
Yeah.
Yep. It's painful.
Are you?
Yeah. And then you get 120.
Oh, there you go. I didn't see that answer. That's why. Fuck. Okay.
My question is, in the multiple choice up there, D, answer D. That's the answer, right?
Yeah.
What happened to the 6 ohms?
True.
You're
Since it doesn't matter, right? Since we
Not
just
really.
find the voltage across that terminal.
Yeah.
Okay.
Okay. Let's do it.
So you found your V Thevenin, right?
Yeah.
Now we have to find our R Thevenin?
I mean, sure, but okay. To do,
I guess it's
yeah.
a stupid question because, I mean,
No, but if you want to do it, because they might trick you and be like 2 with 2 120s. So if you want to find your R equivalent, just open up this this wire, this current source, and then you're left with 12.
So you never count the 6, right? Because I mean, so the 6 doesn't matter like at all.
No, not
You
really.
just
I mean, if it was a voltage source, I think it would.
And it says that D's the answer?
Yeah.
wait.
Okay, cool.
Like, let's say if it was a 10 voltage source or something, whatever, then I'd change it to current using the thingy law. So it's a current in parallel with resistance, and then add them up, and then open it. You guys know source transformation?
Yeah.
Yeah, I do that. I think that's how you do it.
When, the current's in parallel with the resistor, or when the voltage source is in series with the resistor.
I completely forgot what source transformation was.
Okay. Yeah. Because when you do source transformation, instead of being parallel, it changes it to series, no?
Yeah, but that's if the current source was a voltage source. Like that's when it would that 6 ohms right here would matter.
Yeah. Okay. I see.
Help. So sorry.
Are you good?
I'm lost. Okay, so when I see Thevenin, I get automatically scared. So how should I attack this? Like, or like, what is like my first step? I guess I'm gonna say once I see a Thevenin circuit.
So the first step I did was read the question. It's like, okay, we want a Thevenin between A and B. So it marks it for us. And then, so what I did is annotate, draw. Okay, so now I mark A, and then I mark B, right?
Yes.
And then from there it says looking to the left of the following circuit. So we want this. This is what we want right here. So this RL goes bye-bye. It's open, and it's just
okay. Yeah.
Now it's just a one loop thing, right? Just a one loop with a current source, and then it's easier because all the answers have different voltages. So now you just have to find the voltage across A and B. So
okay.
What's across A and B? Which resistor?
The 12.
There you go. So if it's one loop,
Okay.
Current.
Okay.
12 ohms.
Oh, so that 6 isn't part of A and B. Oh, okay.
Okay, yeah, this brings back to Breezy. Okay, yeah.
I told you a zillion times.
Simple KCL.
Is there an example? Damn it. Okay.
Thank you, Justin.
Yeah, of course.
Anyone else? Any questions?
Any questions?
Yeah, so let's say if it was a voltage source, the Thevenin equivalent circuit that you would be looking for would be converted into a current source?
You can do that. Let's say it's like 12 volts. 12 volts plus or minus. And also someone double check me on my source transformation. So 12, 6, it'd be V, pretend that's a V, equals IR. So I is going to equal 12 over 6. So it's going to be 2, erase that. And then it's going to be in parallel with 6, in parallel with 12. And that would be your almost Thevenin.
Mm-hmm.
That would be your terminal. A, B. That's how I'd approach it if this was a voltage source.
Oh, because of source transformation.
Yeah.
Oh yeah. Okay, I see it. Okay.
Mm-hmm.
That answer your question, hopefully.
Yeah, yeah. I'm just working it out, but yeah, I did. Thank you.
Any more questions? Feel free.
10 to.
No? All good? All right. And if you have any questions or you want to go back or anything, just let us know. All right. So we can move on to the next one. So this one right here. Go ahead and it's bigger. So size the resistor RL to allow maximum power transfer through.
Yeah, this is, I could do this one. This is a circuits 2 one.
Oh shit, this is circuits 2?
Yeah, so this is kind of a little bit more advanced topic, number 4 and number 5. But I mean, I could show them just in case they come up. I mean, just to give you guys a little background on circuits 2. So if you want, I could share my screen.
Yes, sir.
I'll get started. One sec. Okay. Can everybody see?
Yep.
Okay. So when we're dealing with, okay, the question is asking size the resistor so that we want to allow maximum power transfer. So there are like 4 cases when we're dealing with max power transfer. There's like DC resistive, then there's like inductor, I think it's like, I forgot what the other terms are, but for this case, we're dealing with a DC resistive circuit because there are only resistors in this circuit, obviously.
Mm-hmm.
And the formula for when you're finding max power transfer, it's pretty much what we're going to be using here is R Thevenin is going to be equal to R load. This formula only works in a DC resistive circuit when we're dealing with max power transfer, and we want to find you know, our max power for the circuit. So this is another, like, I guess, Thevenin one. So what you have to do here is, so the first step, I guess you could redraw the circuit.
Mm-hmm.
Okay. And if you guys have a bunch of questions, I understand, because this is like there's a lot of background you have to know on this. And I don't think we're expecting anybody to have background in this yet. This is like a late game question. So, okay, so this is what it looks like. So the first thing we have to do is find the Thevenin of this circuit. So does anybody know what I should do first?
Ignore right.
Off RL?
Transformation.
Ignore the right side, right? So we're gonna set this open and we're gonna erase partial. We're gonna erase this right side right here. So it's totally gone. Okay, we're gonna open the circuit, and now we're gonna look at the circuit from the outside right here, right? What else do I need to do?
We did it last time too, for the last
Kill
example.
the source.
Right, we have to kill the source. So what happens what happens to a DC source? Is it short or is it open?
Open.
Wrong. It shorts. So I guess we should write it up here.
God damn.
So for Thevenin,
Fail me already, man.
it's okay. For Thevenin,
It's okay. Did you hear
it's
that?
okay, bro. That's what we're here for. We're gonna short, and for current sources, we're gonna open. It's
Think about it
very
this way. What
important to
happens when you
know.
have 0 volts?
Yes. Oh, when you have 0 volts, yeah. Well, that's another topic. Jesus Christ. Okay, so that brings me nightmares. Here we go. Just remember that. That's very important to know, because then you'll get Shrek. So now it becomes an easy peasy circuit that we just have to solve for. Since we are looking for RL, all we have to do is find our Thevenin, and we can easily find our Thevenin now. So, am I going too fast?
Good, I'm following.
No.
Good? Okay.
Go ahead.
Our Thevenin is going to be equal to what?
The summation of all the resistors?
Right,
Or,
so what is it?
let's see, so 10, 10.
So 2 and 15 are parallel, I believe, and then series with 10.
Mm-hmm.
Does everybody agree with that?
Yes.
Yes.
I think it's 2 and 15 are parallel, and then you add on with 10.
15 plus 2 parallel with 10.
Okay, so I'm getting 15 in parallel with 2 plus 10, and then I'm getting 15 plus 2 in parallel with 10. I'm getting 2 different things.
Mm-hmm. Mm-hmm.
What if I told you that it's 10 in parallel with 15 plus 2?
That's what I
Would you
was
guys
thinking.
agree with me?
I agree.
Yeah.
That's
Okay.
right.
Okay, so I can explain how we got that. If we just redraw this is actually just looking like maybe that makes it look a little bit better.
Mm-hmm. Mm-hmm.
Right? So
Yeah.
now we can easily see that these two are in parallel, and that one is just going to get added at the end. Does everybody see that?
Yep.
Yeah.
Cool. Okay, now it's just as simple as doing the parallel combination. So we got 10 times 15 over 10 plus 15 plus 2, which is going to give us, I'll just put it in the calculator.
Dang.
8. Yes, 8. And that is correct. So our Thevenin is now equal to our load, which is equal to 8 ohms. And that is our answer, which is B. Any questions?
Can I see the question, Sales? Can you go up a little bit?
There's a bunch of stuff on max power transfer in circuits too. So I think this is a very good problem to remember. Tabrizi goes over it really in depth, but I can't go over it really in depth because I'm not a god. So I'm sorry, but I can give you
Not yet.
how to do it. I'm gonna give you how to do it. But if you have any like theoretical questions, I don't think I can answer a lot of them. So I'm sorry for that, but I can help you. But yeah, I think that's it for 4. Does anybody want to have more questions?
So this topic, was this for exam 3 or 4, or was it
This was
just?
exam 1.
Oh fuck. Okay.
Yes.
What she asked you for one?
Yep.
Mm,
This is like the last part of exam 1, but it might be at the start of exam 2. I think she switches it up.
okay.
Yeah. All right. I'll stop sharing.
Yeah. So I just want to, yeah, I'm gonna start sharing. Let everyone know now that the official time for this, for these FEEIT sessions are going to be from 9 to 10. So you could stay from, it's going to be 10 in like 5 minutes. So if you want to, yeah, so if you want to stay just for the hour, cool. If you want to stay longer, a bunch of us are going to be staying longer. A bunch of the board members are going to be staying longer. And Sebastian and Justin and Matthew are going to be here as well.
Yeah, let's do the whole book.
God damn.
Book right now.
Definitely we should record it. Definitely we should record it.
Yeah, no. So yeah, we're gonna stay, and if you need to go for whatever reason, maybe you sleep, you're tired, whatever, this is gonna still be recorded even after 10 o'clock. Don't worry about it being recorded, or not missing out on any questions. So we're still gonna do it, but if you still want to hang out with it or still want to hang out and do problems with us, you're more than welcome to. Just letting you know. So that's why 9 to 10 are the official times, but we're gonna keep going after 10 o'clock.
Also, guys, if you are leaving right now, it's okay. Like Anthony said, it's okay. We just planned for 1 hour. This was just like a trial, right? But also, before you guys go, we were thinking about next week. We came up with I guess like a mock-up exam for the EIT. So we want to take it next week, and it can give us the results and see where we're missing information. I don't know how many questions it is. I'm not sure if Juan it's on the chat right now. Let me just check.
I don't think Juan's here.
No, okay. So it's just like it's like a practice exam from the EIT. So we want to take it next week. That way we know what are the topics that we're missing. Juan is the president for chess. So he's the one that has access to the practice exam. So we're doing like a collaboration between IEEE and chess. And the idea is that they have a Canvas page where we can, they have a lot of information for the EIT. We are going to take the exam next week. You get your results next week, and then we will take it again at the end of the semester and compare your results for the first exam to the last exam and see if you improve and, help you out with that.
Yeah.
So yeah, if you want to leave, it's okay. We will.
Big things coming up. But yeah, if you want to stay, chill, do some questions, we're gonna be here.
I have a question about the practice exam. We're only taking that once.
We're taking it twice.
Twice, okay. I was about to say, I feel like that would be a good idea to take it more than once.
If you want, if you guys want to take it, like, I don't know, at the middle of the semester, we can do that and do it 3 times. You get me?
Yeah. To get used to the test. I guess like in high school when I took calculus BC, the only reason I passed that shit is because I took that AP test like 3 times practice before I actually went in for the official. So I feel like that's a good plan.
Yeah. So on that note, thank you, Sean. Yeah, we can, if you guys want to take it more times, we can do that. The only, I guess the only thing right now is that since it's going to be a Canvas page that is provided by the university and everything, all the materials provided by chess, in order for you to be part of that Canvas, you have to be an IEEE member. So with that being said, Luis, it's He's the membership coordinator for the club, so he's gonna be handling that on the next few weeks, you know. But as of right now, Anthony has the Google Forms that we need you guys to fill out. So we have your information because in order for us to add you to the Canvas, we need your email, your name, and all of that, and to give you access to all the information. So I guess after the meeting, I don't know, Anthony, you can send it on the IEEE GroupMe, and you guys have to fill it out. Just make sure you guys are a member already. You're good with that, and then yeah, access will be provided by next week.
Yeah, that's really all the announcements that we had.
Yeah.
What?
There you go. All right.
All right. So moving on now. Okay. So we do number 6, resistivity. I think that's more of a. It's more like a.
That's like an EMF problem, but I don't know. Did you want to do 5 too, or you want to go to 6 and then I'll work on 5 right now because that's another circuit.
Hey Sebastian, doesn't that look like a intro to power question? Low key.
A what? Intro to power
/ EMF. Yes. Number 6.
5.
Number 6.
Oh, number 6. Yes, it does. Yeah, it's definitely EMF, like. That's like resistivity and stuff. That's just a formula. That's like a, yeah, maybe when you guys can show them how to do that one.
Yeah, it's
I'll work on number 5 right now.
A lot of the questions in the FE are formula based. So if you get comfortable with the manual, the reference manual, you'll be able to find those formulas, and you know, often it's just a matter of plugging in the right values in the right spot. So if you guys can afford it, I'd highly recommend that you guys get the reference manual. Or Johnny, I think you said we're going to have access to that info, right?
It's free, isn't it?
Well, I bought my own. I have one anyway, but
I mean, online you get it for free.
Then that would be great. You guys can get familiar with it before you take the test. That way you're not wasting time searching for the formula you need. You already know what section it's in.
That's true.
Okay. Yeah.
That's true.
Oh, is it free?
Johnny, I'm gonna send it to you right now.
Okay, there you go. So Devin, I'm assuming they already have it on Canvas. But if not, we can add it. But yeah, thank you. And also, just so you guys know, Matthew, Sebastian, and Justin are gonna be the TAs for the Canvas page. So they're gonna give you guys access. So if you guys can fill out the form as well when Anthony sends it on the GroupMe, that would be really helpful. Thank you.
Area. I think that's the formula. Looks right. Ohm centimeters, ohm times centimeters, and centimeters squared over distance squared is going to be left with the ohms. Yeah, that should be right. And then that's just plug and chug from there.
Oh shit.
Mm-hmm.
All right, so you just find the radius then, because it's a, yep. Find the radius, plug in the area of a circle.
Yeah, I gotta hop off, y'all. I gotta do this assignment.
All right, man.
Forgot about sensors. All right, y'all.
Sure.
Have a good night.
You too.
So.
Okay, let me see.
Okay, I got number 5 if you want to go over it.
So for number 6, just to clarify, because I mean, I already passed this class, but I'm kind of confused. Let me see. So for the P, let me see. Because I remember you had the conversion.
Or it's a row, but I can't.
So that row is 1.83 times 10 to the -6.
Yes.
Oh, that's the row. Oh, yes.
L is that an L or is that an R?
I think it's a L.
L.
Which is the length, no? The 5
Yeah.
kilometers?
5K.
What's the length?
5K. 5 kilometers.
Oh yeah, I'm dumb. Yeah. Got it.
That's good.
Got it.
Hey, let me just work it.
You just blew Johnny's mind right now, bro.
He is a walking reference book, okay?
Oh yeah, that's the formula on the thing. Cool.
Yeah, bro. Wow. Just one simple formula. Fucking chug this little. I know. Justin didn't even need the handbook, dog. He said, fuck the handbook. I'm just gonna do this shit by myself.
They might hire Justin at the EIT exam.
Make everyone suffer.
All right. You good, Johnny?
Yeah.
Everyone good? We're gonna cool to move on to number 5.
Any questions on number 5?
Questions?
Yeah, go ahead, move on.
All right.
Good.
All right, 7.
All right.
I'll get. You can go ahead and.
Okay.
What was the answer for number 6? I think I missed it.
B.
B. Oh.
All right. Everybody see what's going on here?
Sure.
Okay. So the question is, they give us the initial voltage across the capacitor, which is 5 volts. Yes, Ricardo, you are. They give it to you in like a pamphlet. I think it's at the start of the booklet, but I think they give you a separate booklet. I'm not sure.
No, it's electronic now.
Yeah.
Oh, it's electronic. Oh,
Yeah,
well, there you go.
Electronic reference.
Electronic. What the fuck?
I have the physical
Safety.
copy to get familiar with it, but it would be nice if we could find the virtual one to get familiar with that as well.
Okay. I'll see
Yeah.
if you can get it.
I send it to you, Johnny, right now.
Yeah. I'll, that one, but is that one, do they updated it or that's
Yeah, I
the-
downloaded it like a week ago
Oh, okay.
from
Okay.
their website.
Okay, thank you.
Mhm.
I'll send it on the chat as well. So you guys
Sure.
can.
Okay. Are we ready?
Yeah.
Good. Okay. So, yeah, this is called a first order switching circuit. Okay. And the reason why it's called that, it's first order, because there is one element that makes it a first order, which is the capacitor. A first order could also be an inductor as well, but for this case, it happens to be a capacitor. So they tell us at time is equal to 0, the switch is closed. What is the voltage across the capacitor 10 microseconds after the switch is closed? So there's pretty much just this one formula, like with every other problem we've been doing, that solves this for you, okay? So for any first order DC circuit, you can make these, okay, here. This is the formula right here. So you get x of t is equal to x of 0 plus, and I'll explain this right now, x of 0 plus minus x infinity, e times that, and then plus x infinity, okay? And your key values are right there as stated. And this is for t is greater than or equal to 0. Okay, I'll let you guys copy that real quick. It's a very important formula to have for switching circuits. And I'll explain.
You have to
why.
remember, or do they give
Yes. No. They should give you this, but this might be something that you remember, because this is like, it's just one of those formulas where you keep seeing it all the time. It's going to be like V equals IR type of thing to you. So definitely get familiar
Yes,
with it.
they do have they do have it on the reference manual. It's under RC and RL transients.
Okay, there you go. Yeah, should be under,
Thank you.
yeah, transient circuits and stuff. Okay,
Thank you, guys.
so, okay, so the question is, I guess the problem in question is the voltage across the capacitor 10 microseconds after the switch is closed. So what you want to do is, first off, I guess pay attention to your circuit, right? You can model this equation right here to use for any type of or question that they're asking for. So sometimes they might ask you for the current across the capacitor, the current across the inductor, et cetera, et cetera. So there's X's because that's the primary reason why. So in this case, since we're looking for voltage, we're going to switch those X's to V's. Okay.
Mm-hmm.
Okay. So, and I can give an example for current as well. T and then tau plus V of C infinity. Okay. I'll let everybody write that. Oh, write that real quick.
Mm-hmm.
So this is like step one. You know, I'm gonna put this on the side, sorry. There you go. Okay, cool. All right, we're good? Everybody got that right now?
Yeah.
Okay, so this is a switching circuit. So we're gonna do what a switching circuit does. It has a couple states to it. So what this means is that before the switch closes, we can see that they told us that there was initial voltage across the capacitor. Oops, I highlighted too much. At 5 volts, okay? So when we're looking at this equation, there's a couple key things that we have to look at. So we're looking for the key values, right? So when they give you an initial voltage or something, or initial anything, so let's say, I'll write a little note right here. When initial value is given, that value will be your X0 plus, okay?
Mm. Mm-hmm.
Okay. All right, so in this case, they told us that, what did they say? The initial voltage was 5 volts, so that means that our VC0 plus is going to be 5 volts, okay?
Mm-hmm.
Now, okay, now the reason why they give us an initial value is because right after, so we kind of have to like visualize this, kind of just picture this, okay? So right after the switch is closed, right here, right after the switch is closed, there's a current going through this, I mean, yeah, there's a instantaneous time where the voltage across the capacitor is going to be equal to 5 volts, and only for that moment. So that's why we have to include that instantaneous time value right here, where VC0 plus. VC0 plus means that, or it's just giving us that instantaneous value right when the switch is closed, okay? So that's the only reason why we need that initial value. Okay, so, and then you might be wondering, oh, well, Sebastian, how do we get VC infinite? Okay, so right after the switch has been closed, it's not, we're not looking at that initial voltage value anymore. We're looking at what the voltage is going through the circuit, okay? So since this is actually pretty easy because they actually give us a DC source right here. Okay, and that DC source is going to continue giving us 10 volts as long as this switch is closed. And since we're not looking for the instantaneous time when the switch is closed, our VC infinite is going to be 10 volts. Okay, so long as the switch has been closed, VC infinite is going to be 10 volts. Okay, do you have any questions right now? Sorry, there might be a lot to take in. I know it sounds very foreign, but this is good that you guys are learning this now. That way you might be a little bit ready for circuits 2. Hello?
Yeah.
Oh, okay.
We hear you. We hear you.
Yeah.
I don't know who's.
I'm just
Okay.
taking all the information.
Yeah,
Just
I know
subbing.
it's a lot. It's a lot. I know. Okay, so can I proceed?
Yeah, I mean,
Okay.
Yep.
So we got our key values, or at least 2 of them. We got VC is equal to 5 volts, VC infinite is equal to 10 volts. If maybe you want, here, maybe I write a little note. Initial value given. And this is actually, the name for this is actually the steady state value. And this is after switch has closed for a very long time. Okay. I'll let you guys copy that real quick. Tell me when you're ready. Give me like a thumbs up, I guess. I don't know. Should I zoom in? Are we good?
I'm good. I don't know about
Yes.
Good to go.
Okay.
Okay. So moving on. You notice that our key values we found, we're almost done. We just need our tau. So if anybody remembers, does anybody know what tau is equal to?
1 over. No. Let me see. I don't know, bro.
It's just RC, exactly. Yes, thank you, Caesar. Yes, tau is equal to RC. Okay. Okay. So now we have our key values. We're able to plug everything into our preliminary equation. Okay. Sorry. So our equation is going to be 5 Okay. Everybody understand what I just did there? All I did was plug in the values that we had into our equation, right? Oh, also tau. I just plugged it in right there. Tau is just right here. Okay. I hope I didn't do this backwards. I feel like I did this backwards right here. I'm going to check. I know I have the answer right here, but did I do it backwards? I don't think so. I hope I didn't. But anyways, did I do it? Sorry, I'm just kind of debating with myself. I'm not sure if this is supposed to be switched around, but I guess we'll find out right now. Okay, so now We are also given our RC values for the circuit, so we could just plug those in as well. So if we want to simplify the circuit some more, what is R and C? We got 10 for R. And then for C, we have 1 microfarad. Okay. So now we're going to be left with 10 times 1 microfarad right there. And that's going to equal to plus 10. Okay. So now we're left with our one equation. Okay. And from this equation, we're able to answer the question at hand. As long as we did everything right, which I presume we did. And they gave us the time in the beginning. They gave us the time to be, what is the voltage across the capacitor? 10 microseconds after the switch is closed. So time here is going to be 10 microseconds. Okay. So now we just plug it in to find the voltage. Okay. Now you do a bunch of math. Let's see if we did this right. Hold up. I'm going to plug this in my calculator. I feel like I might have gotten something backwards here. Hopefully not. All right. And I get 8.16 volts. Okay. And that is actually our answer. So we did everything right. Cool. Any questions here?
I have a question, I guess not regarding the shape, but for the exam, do you guys know if what kind of calculator do they let you take, or what is it?
They let you use the one that we use, the Casio one.
Or you can take your
The
Yeah.
TI 36 too.
Yeah.
okay. The God calculator.
The God
The God calculator. Yeah. Highly recommend.
I'm making sure, guys.
Yeah. But yeah, that's how you do this one. Just a little glimpse into your future.
Oh God.
Sebastian, can you go back to the original question really quick, please?
Yeah.
Oh, okay.
Yeah. Remember this. Remember, it's called a first order switching circuit.
Okay.
Quick question. The recording is gonna be. This one's also gonna be posted on, like you said, the YouTube channel.
Yeah.
YouTube channel.
Thank you.
We do now.
Need a podcast too.
All right. Are we good?
Gucci?
Yeah.
Okay.
Yeah.
Wait.
Go ahead.
All right. Let me see. Is that the last one for that page? I believe that is the last one for that page. Well, the next page.
What's up, guys?
What happened?
So what's up, guys?
Oh, what's up, bro?
What's up, Derek?
What's up, Derek?
What's up, bro?
Hiding in the shadows.
Yeah. You guys going through the exam or?
Yeah. Yep. Going through the FE manual.
Where'd you guys?
All right. So, what's up?
Where'd you get the practice exam?
Sean.
Okay.
Sean plugged it up for us. All right. So number 7. Actually, Justin, do you want to handle number 7, or do you want to?
Oh, number 7 is pretty simple. It's just I squared r.
P equals I squared r.
Yeah, you don't want to get confused with this 10 kV because like technically the 10 kV is not like directly across that transmission line.
Mm-hmm.
So I think the better would be like that's it. You have a source, it's your 10 kV, and then you have your line, and then whatever load. Then you got your I, and you got your 0.7 ohms. This is kind of inconsequential. Then I squared r, get your power. I went through that super fast, but like, you guys see that? Questions?
Wait, what the fuck?
Yeah, bro. Johnny, I'm with you.
Okay, so basically, to break it down, it's like they give us 10K, there's the voltage.
Mm-hmm.
We have a total resistance, 7 ohms, and we have a current flowing through. It's 10 amps.
Mm-hmm.
Right? So what they want is what is power dissipated. So we know we can do this one of 2 ways. We can do V squared over R. It's going to be 10K, or 10 mega in this case, over 0.7. But we get like an insanely huge number, so that's not going to make sense. So our other option is P equals I squared over R.
Mm-hmm.
So that's going to be 100 divided by 0.7. Or 100 times, no, not over R, I squared times R. There you go. Maybe that first one didn't look right. I squared times R.
Okay.
So you do 100 times 0.7 and you get 70s right there. This whole example thing, it's like, it's just to tell you why this one doesn't make sense.
Okay.
All right. Okay.
But do you guys get like why we use I squared R?
Like, why are we using that formula instead of the other ones?
Yeah.
Good question.
Is it because we're looking for power dissipated in the line? So current?
Exactly. Right. So your line is going to be in series with whatever like load or other transformer or whatever is at the end of it.
Mm-hmm. Mm-hmm. Mm-hmm.
All right. Got it. Everyone good? Everyone good on this problem?
Yeah. Yeah, I think so.
All right. Perfect. So
Yo, I'm gonna log off. I gotta wrap up this lab report.
All right. Yeah.
for sure, Matthew.
Both left me.
I'll catch you guys in the next one.
For sure, dude. Thank you. Thanks,
We'll go on, guys.
dude.
Bye.
Honestly.
Yeah. If you, I don't know, Anthony, if you wanna stop it here. What do you think?
Yeah, I think we
Yeah.
covered a good amount today.
Be like an hour and 30.
That's cool.
7 questions.
Anthony was saying we're gonna go to midnight.
We could if you guys want.
So early in the semester, we're like,
Yeah, this is like a, beginning, introduction.
Yeah.
That'll be an introduction, but okay, we all need rest.
Yeah.
Yeah.
No, I agree.
This is a good
Nice.
refresher. Thank you.
Yeah.
Yeah.
Thank you. Mm-hmm.
Gonna hopefully go a little bit more smooth, like after we keep doing this. So
Yeah. This was just like a trial, but yeah, like I said, the plan is like to take the practice exam next week. So be ready for that.
yeah, 100%. All right, so I'm gonna go ahead and